In February 2025, Russia's state nuclear corporation Rosatom announced the completion of a laboratory prototype plasma electric rocket engine that could reduce travel time to Mars from the conventional 6 to 9 months down to 1 or 2 months. This is not speculation or theoretical physics. This is a working prototype currently undergoing ground testing in a vacuum chamber designed to simulate space conditions. The announcement came from Alexei Voronov, first Deputy General Director for Science at Rosatom's Troitsk Institute for Innovative and Thermonuclear Research, and the prototype's existence has been confirmed through official press releases from Atom Media, Rosatom's affiliated media outlet. In early 2025, the measured performance parameters are specific. The engine produces at least 6 newtons of thrust and operates with a specific impulse of at least 100 kilometers per second. It draws an average power of 300 kilowatts when operating in pulsed periodic mode. Previous testing demonstrated an engine resource exceeding 2400 hours, which engineers calculate as sufficient for a complete Mars transportation operation. These are not projections. These are test results from a physical device. If you enjoy this kind of evidence-based content, like the video, subscribe to the channel, and turn on notifications. There are many other videos on the channel built the same way, and if this topic interests you, you'll likely enjoy what's already there. The reason this matters becomes clear when you understand conventional Mars mission architecture. Current spacecraft traveling to Mars using chemical propulsion follow what is called a Hohmann transfer orbit, the most fuel-efficient trajectory between Earth and Mars. This elliptical path around the Sun intersects Earth's orbit at launch and Mars' orbit at arrival. The spacecraft accelerates once to enter the transfer orbit, then coasts for months, then decelerates to enter Mars' orbit. The duration of this journey is determined by orbital mechanics, not by choice. A Hohmann transfer to Mars takes approximately 259 days, or roughly 8.5 months. NASA's Perseverance rover, launched in July 2020, took about 7 months to reach Mars using this approach. This timeline is dictated by the physics of elliptical orbits described by Kepler's laws. The period of the Hohmann transfer orbit is 517 days, and the Mars-bound portion covers half of that orbit. The problem with this timeline extends beyond mere inconvenience. Astronauts on a 6 to 9 month journey are exposed to galactic cosmic radiation and solar particle events throughout the entire transit. Earth's magnetic field and atmosphere shield us from most of this radiation on the surface. But beyond low Earth orbit, that protection disappears. The human body absorbs radiation damage that accumulates over time. Longer missions mean higher cumulative doses, increasing cancer risk and potentially causing acute radiation sickness if a solar flare occurs during transit. A 30 to 60 day mission using plasma propulsion would reduce this exposure proportionally, cutting radiation dose by a factor of 4 to 9 compared to conventional trajectories. This is not a trivial difference. NASA's career radiation exposure limits for astronauts are measured in millisieverts, and every day in deep space adds to that total. But the Russian plasma engine's performance numbers suggest it operates on fundamentally different principles than chemical rockets. Chemical propulsion works through combustion. Liquid hydrogen and liquid oxygen mix in a combustion chamber, ignite, and the resulting hot gases expand through a nozzle to produce thrust. The maximum exhaust velocity achievable through chemical combustion is limited by the energy released in breaking and forming chemical bonds, typically around 4.5 kilometers per second for hydrogen-oxygen engines. This is a hard physical limit. You cannot make chemical fuel burn hotter than its chemistry allows. Specific impulse, which measures how efficiently a rocket uses propellant, typically reaches about 450 seconds for the best chemical engines like the RL-10. This means that for every second of operation, 1 kilogram of propellant produces 450 newton-seconds of impulse. The Rosatom plasma engine bypasses this constraint entirely. Instead of burning fuel, it accelerates charged particles using electromagnetic fields. The prototype uses hydrogen gas as propellant. When high voltage is applied between 2 electrodes inside the engine, the hydrogen atoms are ionized, meaning electrons are stripped away, leaving positively charged protons and free electrons. This ionized gas is plasma. An electric current flowing through this plasma generates a magnetic field, and the interaction between the current and the magnetic field produces a force that expels the plasma particles out of the engine at extremely high velocity. The specific impulse reported is 100 kilometers per second, which translates to approximately 10,000 seconds when expressed in the conventional units. This is more than 20 times higher than the best chemical rockets. To understand what this means in practice, consider the rocket equation. The change in velocity a spacecraft can achieve depends on the exhaust velocity of the engine and the ratio of initial mass to final mass. Higher exhaust velocity means you need less propellant to achieve the same velocity change. The Rosatom engine's 100 km per second exhaust velocity means a spacecraft can reach much higher speeds with less propellant mass, or alternatively, carry more payload for the same propellant budget. This is the fundamental advantage that makes rapid Mars transit feasible. But 6 newtons of thrust sounds minuscule compared to chemical rockets. For perspective, 6 newtons is roughly the force needed to hold a small apple against Earth's gravity. The Space Shuttle's main engines produced about 5 million newtons of thrust at liftoff. How can 6 newtons possibly propel a spacecraft to Mars faster than engines a million times more powerful? The answer lies in continuous operation versus impulsive burns. Chemical rockets produce enormous thrust for short periods, limited by propellant mass they can carry. After the initial acceleration, the spacecraft coasts. Plasma engines produce small thrust continuously for months or years. The spacecraft accelerates slowly but persistently, gradually building up velocity over the entire journey. Consider the mathematics. If a spacecraft with a mass of 1,000 kilograms experiences 6 newtons of continuous thrust, it accelerates at 0.006 meters per second squared. This seems negligible, but maintained continuously for 30 days, that acceleration produces a velocity change of about 15.5 kilometers per second. For comparison, escaping Earth's gravity well requires about 11 kilometers per second from the surface. The continuous thrust allows the spacecraft to spiral outward from Earth, then accelerate toward Mars, reaching velocities far higher than achievable with the brief burns of chemical propulsion. The trajectory is no longer a passive Hohmann ellipse but an active spiral that can be optimized for speed rather than fuel efficiency. However, this introduces severe engineering constraints. The Rosatom prototype operates at 300 kilowatts average power in pulsed mode. 300 kilowatts is substantial. A typical household in the United States uses about 1 kilowatt on average. But where does this power come from in space? Solar panels degrade with distance from the sun and become impractical for high-power applications beyond Mars orbit. The only viable option for sustained 300 kilowatt power output on a deep space mission is a nuclear reactor. Rosatom's involvement is not coincidental. They are a nuclear energy corporation. The plasma engine is part of their broader program developing nuclear power systems for space, which includes work that began in 2021 under Russia's comprehensive program for advancing nuclear science and technology. Space nuclear reactors are not hypothetical. The Soviet Union launched 31 BS-5 fission reactors aboard Rorsat radar satellites between 1967 and 1988. Producing about 2 kilowatts each. The Topaz reactors developed in the 1980s reached 5 kilowatts electric output, making Topaz I the most powerful nuclear system known to have operated in space. But 300 kilowatts represents a significant scale-up. Current development programs aim for this power range. The United States Kilo Power Reactor demonstration in 2018 tested a design targeting 10 kilowatts. Lockheed Martin's Jetson program, awarded in 2023, aims for 6 to 20 kilowatts. China announced progress in 2024 on a 1.5 megawatt reactor designed for space applications. Russia itself has been developing megawatt-class nuclear space power systems since 2010, with plans for operational deployment around 2030. A 300 kilowatt reactor for the Rosatom plasma engine would need to operate reliably for the entire mission duration. The 2,400-hour operational lifetime demonstrated in testing translates to 100 days of continuous operation, which is sufficient for a 60-day Mars transit with margin. But this assumes perfect reliability. Space-rated nuclear reactors must survive launch vibrations, radiation exposure, thermal cycling, and vacuum conditions. They must reject waste heat efficiently without air or water cooling. In space, heat can only be radiated away, requiring large radiator surfaces. A 300 kilowatt reactor might reject 400 to 600 kilowatts of waste heat, depending on conversion efficiency. Radiators for this heat load would be physically large, adding mass and complexity to the spacecraft. The mass budget is critical. A spacecraft's dry mass includes the reactor, the plasma engine, propellant tanks, structure, avionics, life support if crewed, and payload. The propellant mass depends on the mission delta V and the specific impulse. For a rapid Mars transfer using plasma propulsion, the total delta V might be on the order of 20 km per second, including escape from Earth orbit, the interplanetary transfer, and Mars orbit insertion. Using the rocket equation with a specific impulse of 10,000 seconds, achieving 20 km per second delta V requires a propellant mass fraction of about 86%. This means for every 100 kilograms of total initial mass, 86 kilograms is propellant and 14 kilograms is everything else. For a crewed mission carrying habitats, life support, supplies, and a return vehicle, this becomes extraordinarily challenging. But there is a more fundamental problem with rapid transit trajectories. If a spacecraft continuously accelerates for 30 days to reach Mars, it will arrive at Mars with extremely high velocity relative to the planet. It must then decelerate to enter orbit or land. If the plasma engine provides the deceleration, the spacecraft must carry enough propellant for both acceleration and deceleration, doubling the propellant requirement. Alternatively, the spacecraft could use aerobraking, entering Mars' thin atmosphere at high speed and using atmospheric friction to slow down. But entry velocities for a 30-day transfer would be far higher than for conventional homeland transfers. NASA's Mars Science Laboratory, carrying the Curiosity rover, entered Mars' atmosphere at about 5.9 kilometers per second. A spacecraft arriving from a rapid plasma-powered transfer might approach at 15 to 20 kilometers per second. The heating during atmospheric entry scales with the cube of velocity. Entry at 3 times the speed means 27 times the heat flux. The thermal protection system mass would increase substantially, eating into the payload budget. And then there are the biological limits on human crews. The Rosatom engine produces continuous thrust, which means continuous acceleration. If the spacecraft accelerates at 0.006 meters per second squared continuously, astronauts inside would experience a tiny additional force in the direction of thrust, about 0.0006 times Earth's gravity. This is negligible and would not provide useful artificial gravity. For comfortable artificial gravity at 1 Earth gravity, the spacecraft would need to accelerate at 9.8 meters per second squared, requiring 16,000 newtons of thrust for a 1,000 kilogram spacecraft, far beyond the 6 newtons the prototype produces. So the crew would still experience microgravity for the entire mission, with its associated health effects including bone density loss, muscle atrophy, and cardiovascular deconditioning. Higher acceleration could reduce trip time further but introduces G-force problems. Human tolerance for sustained acceleration depends on direction and duration. Acceleration, eyeballs in, with the person lying on their back as in a rocket launch, is best tolerated. Early experiments showed untrained humans could withstand 6G for 10 minutes, or 10G for 1 minute without serious harm. But these are short durations. Sustained acceleration at even 2 or 3G for days or weeks would cause severe physiological stress. Blood circulation becomes difficult. The heart must work harder to pump blood against the acceleration. Tissues compress under the sustained load. One subject who endured 2G for 24 hours in a centrifuge experiment reported extreme fatigue by the end. 3G sustained for the duration of a Mars mission would likely cause serious health damage. So while higher thrust could theoretically enable faster transits, human physiology constrains practical acceleration to well below 1G for missions lasting more than a few hours. This creates a fundamental trade-off. Low acceleration means long flight times but is physiologically tolerable. High acceleration means short flight times but risks crew health. The Rosatom engine's 6 newtons of thrust falls at the low end, producing negligible G-forces. Scaling up to higher thrust requires proportionally more power. A 60-Newton engine would need 3 megawatts. A 600-Newton engine would need 30 megawatts. Each step up demands larger reactors, larger radiators, greater mass, and more complex engineering. At some point, the mass of the power system exceeds the benefit from higher thrust, and mission performance degrades. Existing plasma propulsion technology provides context. Hall effect thrusters have been used on satellites for decades, typically operating at 1 to 2 kilowatts and producing thrust measured in millinewtons. NASA's Next Ion thruster, tested extensively, produces about 300 millinewtons with 7.7 kilowatts of power. The specific impulse reaches about 4,200 seconds, better than chemical rockets, but still below the Rosatom claim. The VASM engine, developed by Ad Astra Rocket Company, aims for variable specific impulse by using radio frequency heating to ionize and accelerate plasma. VASM has demonstrated operation at 200 kilowatts in ground tests, producing about 5 newtons of thrust. The specific impulse can theoretically exceed 5,000 seconds, depending on operating mode, but VASM has not flown in space. An independent peer-reviewed validation of its performance claims has been limited. The Rosatom engine reports 100 km per second exhaust velocity, corresponding to about 10,000 seconds specific impulse, roughly double what VASM claims and more than 4 times what Hall thrusters achieve in practice. If accurate, this represents a genuine advance. But the key phrase is, if accurate. The announcement comes from Rosatom press releases and Russian media sources. No independent scientific publication in a peer-reviewed journal has verified these performance figures. The testing has been conducted in a vacuum chamber at Rosatom's Troitsk facility, measuring 14 meters long and 4 meters in diameter, equipped with vacuum pumping and heat removal systems to simulate space conditions. This is legitimate ground testing, but ground testing in a vacuum chamber is not the same as operating in actual space. Space introduces challenges including thermal extremes, radiation damage to materials, micrometeorite impacts, and the complete absence of atmospheric pressure or convective cooling. Until the engine operates on an actual space mission, its real-world performance remains uncertain. Russia's track record with space nuclear power includes both successes and failures. The BS-5 reactors flew successfully for years. The Topaz program demonstrated functional space reactors. But the Cosmos 954 satellite, powered by a nuclear reactor, re-entered uncontrollably in 1978 and scattered radioactive debris across northern Canada, requiring extensive cleanup. Space nuclear systems carry inherent risks. A launch accident could disperse radioactive material. Reactor failure in orbit could create long-lived radioactive debris. International regulations and safety protocols exist to minimize these risks, but they cannot eliminate them entirely. Any mission flying a nuclear-powered plasma propulsion system would require extensive safety analysis, redundant containment systems, and orbital placement in stable, non-decaying orbits far from Earth to prevent uncontrolled re-entry. Cost is another significant barrier. Developing, testing, and qualifying a space-rated nuclear reactor costs billions of dollars. The Nerva nuclear thermal rocket program in the 1960s and 1970s cost billions in inflation-adjusted terms and never flew. The Prometheus program, initiated by NASA in 2003 to develop nuclear electric propulsion, was cancelled in 2005 after spending several $100 million. Russia's current development program is part of the New Nuclear and Energy Technologies national initiative launched in 2025, with funding coming from government budgets. The timeline for a flight-ready engine is projected around 2030 according to the scientific advisor Konstantin Gudurov. That is 5 years away at minimum, and space programs routinely experience delays. Actual deployment on a Mars mission would likely be later still, possibly 2035 or beyond, depending on integration with spacecraft systems, mission planning, and budget availability. Comparing this to other approaches clarifies the landscape. SpaceX is developing Starship for Mars missions using chemical propulsion. A recent study published in Scientific Reports in May 2025 showed that with orbital refueling and optimized trajectories, Starship could potentially reach Mars in 90 days using conventional chemical rockets, accepting higher delta-V costs, but avoiding the need for nuclear power or improving propulsion systems. 90 days is in the same ballpark as the 30 to 60 days claimed for the Rosatom plasma engine, achieved through different means. Chemical propulsion is well understood, extensively flight-proven, and does not require nuclear reactors. The trade-off is much higher propellant mass. Starship would need multiple orbital refuelings to load enough propellant for a 90-day Mars transfer. But this is engineering we know how to do. Orbital refueling is challenging but not speculative. Nuclear thermal propulsion offers another middle ground. Nuclear thermal rockets heat hydrogen propellant using a fission reactor, producing exhaust velocities around 900 seconds specific impulse, double that of chemical rockets, but far below plasma systems. NASA has renewed interest in nuclear thermal propulsion for Mars missions. DARPA's Draco program, partnered with Lockheed Martin, aims for an in-space demonstration of nuclear thermal propulsion by 2027. Nuclear thermal provides better performance than chemical propulsion and higher thrust than electric propulsion, potentially enabling Mars transfers around 150 days. It also avoids some complexities of plasma engines, operating with technology partly validated in the NERVA program decades ago. Each approach has advantages and drawbacks. Chemical propulsion is proven but requires enormous propellant mass. Nuclear thermal offers better efficiency and higher thrust but involves untested modern reactor designs. Plasma electric propulsion promises the highest efficiency but produces low thrust, requires large power systems, and has limited flight heritage. The Rosatom engine falls into this third category. If its performance claims hold up under independent verification and if the supporting nuclear power system can be developed reliably and affordably, it could enable rapid interplanetary missions. But those are significant ifs. Consider the actual mission architecture required. A crewed Mars mission using the Rosatom plasma engine would begin with launch from Earth using conventional chemical rockets. The engine cannot provide enough thrust to escape Earth's gravity from the surface. The spacecraft would be assembled in low Earth orbit, possibly requiring multiple launches to deliver all components. The nuclear reactor would be inactive during launch and assembly, only starting up once the spacecraft is in a stable orbit well above Earth's atmosphere to minimize risk in case of malfunction. Once operational, the plasma engine would fire continuously, spiraling the spacecraft outward from Earth orbit over several days or weeks, gradually increasing velocity and altitude until escaping Earth's gravitational influence. During the interplanetary cruise phase, the engine would continue firing, accelerating the spacecraft toward Mars. The trajectory would not be a simple Hohmann ellipse but a spiral path shaped by continuous thrust. Navigation would require constant monitoring and adjustment, since the engine is providing thrust throughout the journey rather than just during brief burns. After 30 to 60 days, depending on the specific trajectory and engine performance, the spacecraft would approach Mars at high velocity. If using the engine for deceleration, it would flip orientation 180 degrees and begin firing in the opposite direction, gradually slowing down over several days or weeks until reaching a velocity compatible with Mars orbit insertion. Alternatively, if mass budget allows, the spacecraft could use chemical propulsion for Mars orbit insertion, carrying dedicated propellant for that maneuver. Landing crew on Mars and returning them to Earth adds further complexity. The return journey would require either refueling at Mars using in-situ resource utilization, which is technologically demanding and unproven at scale, or carrying all return propellant from Earth, dramatically increasing initial mass. If the plasma engine is used for the return trip, all propellant for both legs must be carried from Earth unless Mars-based propellant production is available. A complete round-trip mission architecture using plasma propulsion would likely span 18 to 24 months total, including surface stay time on Mars dictated by orbital alignment for the return window, even if each transit leg takes only 1 to 2 months. Radiation shielding for the crew adds yet more mass. Galactic cosmic rays consist of high-energy protons and heavier nuclei that penetrate materials easily. Effective shielding requires significant mass, typically hydrogen-rich materials like water or polyethylene. A crewed spacecraft might need several tons of shielding material surrounding the crew habitat to reduce radiation exposure to acceptable levels. Shorter transit time helps by reducing total exposure duration, but the shielding mass requirement does not disappear. The spacecraft still needs to protect the crew for the weeks they are in deep space, plus the time spent on Mars' surface where the thin atmosphere provides minimal protection. Thermal management becomes critical with a 300 kilowatt reactor operating continuously for months. In space, the only way to reject heat is through thermal radiation. Radiators must be large enough to dissipate waste heat without overheating. The Stefan-Boltzmann law governs radiative heat transfer, with radiated power proportional to surface area and the fourth power of temperature. Operating at higher temperatures allows smaller radiators but requires materials that can withstand those temperatures without degrading. Typical space radiators operate around 300 to 400 Kelvin. At 400 Kelvin, radiating 600 kilowatts of waste heat requires roughly 150 square meters of radiator surface, assuming emissivity close to 1. That is a radiator panel about 12 meters by 12 meters. Multiple panels might be needed for geometric reasons and redundancy. These radiators add mass, structural complexity, and deployment mechanisms. Power conversion efficiency matters enormously. If the reactor produces 300 kilowatts thermal output and the conversion system is 33% efficient, only 100 kilowatts reaches the plasma engine and 200 kilowatts must be rejected as waste heat. Higher efficiency reduces the radiator size requirement. The conversion system might use Brayton cycle turbines, Stirling engines, or thermoelectric generators. Each has different efficiency, mass, and reliability characteristics. Brayton cycles can reach 40% efficiency with advanced designs. Stirling engines can achieve similar performance in small-scale demonstrations. Thermoelectrics are simpler and more reliable but typically limited to 10 to 15% efficiency, which would be inadequate for this application. All these subsystems must work together reliably for the entire mission. A single point failure in the reactor, power conversion, thermal management, or propulsion system could jeopardize the mission. Redundancy is essential but adds mass and cost. The spacecraft must carry backup systems, spare parts, and diagnostic equipment to detect and correct failures. For a crewed mission, crew safety is paramount. The reactor must have multiple independent shutdown systems. The life support must function even if primary power is lost, requiring backup batteries or solar panels. The propulsion system must be controllable from multiple command paths to prevent loss of attitude control. And all of this assumes the performance numbers reported by Rosatom are accurate and reproducible in flight conditions. Until independent verification occurs, we should maintain appropriate skepticism. Claims of breakthrough performance are common in space technology development. Many fail to materialize. The VASM engine has been in development for over 25 years and has not yet flown in space despite numerous demonstrations and performance claims. The M drive, which claimed to produce thrust without expelling propellant, was thoroughly tested and found to produce no actual thrust after accounting for experimental errors. Cold fusion promised limitless energy in 1989 and turned out to be irreproducible. Skepticism is scientifically warranted until claims are independently validated. That said, Rosatom is a legitimate organization with real expertise in nuclear engineering. Russia has a history of functional space nuclear systems. The prototype exists and is undergoing testing. The reported performance, while ambitious, is not physically impossible. Plasma acceleration to 100 km per second is feasible given sufficient power density and magnetic field strength. The challenge lies in engineering a system that achieves this performance reliably at scale in the space environment, while managing heat, mass, power, and propellant efficiently. If successful, the implications would be substantial. 30 to 60-day Mars transits would reduce crew radiation exposure significantly compared to conventional missions. This could make the difference between acceptable and unacceptable cumulative dose for career astronauts. Faster transits also reduce time in microgravity, lessening physiological deconditioning. Shorter missions reduce life support consumables mass including food, water, and air recycling system capacity. Psychologically, a 2-month mission is much easier to endure than a 9-month journey in a confined spacecraft. Rapid transit also opens possibilities for abort and return scenarios. If a crew encounters a serious problem shortly after leaving Earth on a conventional homing trajectory, they cannot simply turn around. They must continue to Mars, a 6 to 9 month journey with a disabled spacecraft. With continuous thrust propulsion, the spacecraft could potentially abort the mission and return to Earth sooner, depending on when the problem occurs and remaining propellant. This flexibility improves mission safety. For cargo missions, shorter transits mean less time for equipment to degrade in the space environment before arriving at Mars. Radiation exposure damages electronics over time. Shorter transits reduce this cumulative damage. Cargo does not care about G-forces or radiation dose limits, so cargo missions could potentially use higher acceleration and shorter flight times than crewed missions, perhaps reaching Mars in 3 to 4 weeks if propellant budget allows. But we should be clear about the timeline. The Rosatom prototype is currently undergoing ground testing. It has not been integrated into a spacecraft. It has not flown in space. The nuclear reactor to power it has not been built. The spacecraft to carry it has not been designed. Mission planning for a Mars mission using this technology has not been completed. The projected timeline for a flight-ready engine is around 2030. An actual deployment on a Mars mission would come later. This is not imminent technology. This is a development program with a timeline measured in years to decades. Other nations are pursuing similar capabilities. China's 1.5 megawatt space reactor program, if successful, could power even more capable plasma propulsion systems. NASA's renewed interest in nuclear thermal and nuclear electric propulsion could yield operational systems in similar timeframes. SpaceX's approach with Starship using chemical propulsion and orbital refueling could achieve comparable transit times without requiring nuclear power. The landscape of Mars mission technology is competitive and rapidly evolving. The Rosatom announcement is significant because it represents tangible progress toward high-performance electric propulsion. 6 newtons of thrust at 300 kilowatts with 100 kilometers per second exhaust velocity, if verified, would represent state-of-the-art performance for plasma thrusters. The 2,400-hour operational lifetime demonstrated in testing shows durability sufficient for interplanetary missions. The existence of a physical prototype in ground testing shows this is not mere paper design but actual hardware development. But converting a laboratory prototype into a flight-qualified space system is a long, expensive, and difficult process. Every component must be space-rated. Every failure mode must be analyzed. Thermal vacuum testing must validate performance in simulated space conditions. Vibration testing must confirm survival of launch loads. Radiation testing must ensure long-term reliability in the space environment. Integration with spacecraft systems must be demonstrated. Mission simulations must validate operational procedures. All of this takes years and requires sustained funding and technical effort. History suggests caution. The Soviet N-1 rocket, intended to send cosmonauts to the Moon, failed in all 4 launch attempts between 1969 and 1972, and the program was cancelled. The Space Shuttle was supposed to launch 50 times per year at low cost but flew only 135 missions over 30 years at enormous expense. The International Space Station was originally estimated to cost $8 billion and took over a decade longer to complete than planned. Major space programs routinely exceed budgets and schedules. The Rosatom plasma engine program could follow similar patterns. Yet progress in space technology does occur. Reusable rockets were considered impractical for decades until SpaceX demonstrated Falcon 9 booster recovery. Ion propulsion was theoretical until Deep Space One flew in 1998 and demonstrated its viability. The Mars rovers were supposed to last 90 days, but Opportunity operated for 15 years. Breakthroughs happen when engineering persistence meets adequate funding and competent execution. The fundamental physics of plasma propulsion is sound. Accelerating ions electromagnetically can achieve far higher exhaust velocities than chemical combustion allows. This has been known since the 1960s. The challenge has always been generating enough power to produce useful thrust. A 300 kilowatt reactor solves the power problem if it can be made reliable and affordable. The Rosatom prototype suggests this may be achievable, though much work remains. For viewers interested in space propulsion, the key takeaway is that multiple paths to rapid Mars transit exist and are under development. Plasma electric propulsion with nuclear power is one approach, represented by the Rosatom engine. Nuclear thermal propulsion is another, pursued by NASA and DARPA. Advanced chemical propulsion with orbital refueling is a third, exemplified by SpaceX Starship. Each has different technical maturity, performance characteristics, cost profiles, and risk factors. Which approach succeeds first depends on engineering execution, funding availability, and program continuity over the next decade. The Rosatom announcement moves plasma propulsion from theoretical studies into tangible hardware development. That is genuine progress. Whether it leads to operational Mars missions by 2030, or becomes another promising technology that fails to reach flight status remains to be seen. The numbers are encouraging. 6 newtons of thrust, 300 kilowatts power, 100 kilometers per second exhaust velocity, 2,400 hours operational life. If these hold up under independent verification and can be scaled to flight systems, rapid Mars transit using plasma propulsion becomes feasible. But feasibility is not the same as inevitability. Converting prototype hardware into flight missions requires overcoming numerous engineering obstacles, securing sustained funding, navigating regulatory requirements for space nuclear systems, integrating with mission architecture, and demonstrating reliability sufficient for human spaceflight. Each of these is challenging. Collectively, they represent years of development effort. The clearest conclusion we can draw is that the technology exists, in prototype form, to enable Mars missions measured in weeks rather than months. The Rosatom plasma engine demonstrates this is no longer purely theoretical. Whether this particular engine reaches space, or whether other programs deliver similar capabilities first, The trajectory of development is toward faster interplanetary travel. 30-day Mars transits are moving from science fiction toward engineering reality. The timeline is years, not centuries. The physics is established. The engineering is difficult but not impossible. Progress is being made. The specific technical challenges that remain before this technology reaches operational status deserve detailed examination. The vacuum chamber testing at Troitsk provides valuable data, but it cannot fully replicate the space environment. In the vacuum chamber, the engine operates in a controlled setting with nearby walls and support equipment. In actual space, there are no walls. Expelled plasma expands infinitely into vacuum. Electromagnetic interactions behave differently. Thermal radiation is the only heat removal mechanism, with no chamber walls to absorb stray heat. The engine must maintain stable plasma discharge without the stabilizing influence of nearby conductive surfaces. These differences could affect performance in ways not captured by ground testing. Electromagnetic compatibility presents another concern. A 300 kilowatt reactor produces substantial electromagnetic fields. The plasma discharge itself generates additional electromagnetic radiation. These fields can interfere with sensitive electronics, communication systems, navigation sensors, and scientific instruments aboard the spacecraft. Shielding is required to protect critical systems, but shielding adds mass. The engine must be positioned carefully relative to other spacecraft components to minimize interference. Cables carrying high current must be routed and shielded to prevent electromagnetic emissions from disrupting nearby systems. All of this requires careful integration engineering that goes beyond testing the engine in isolation. Propellant storage and feed systems add complexity. Hydrogen, the propellant for the Rosatom engine, is the lightest element and notoriously difficult to store. Liquid hydrogen must be kept below 20 Kelvin to remain liquid. This requires active cooling or thick insulation to prevent boil-up. For a mission lasting 30 to 60 days, storing liquid hydrogen without significant losses is challenging. Boil-off can be minimized but not eliminated. Some designers consider storing hydrogen as a cryogenic liquid and others propose using gaseous hydrogen at higher pressure, accepting the mass penalty of heavier tanks. The propellant feed system must deliver hydrogen to the engine at a controlled rate, maintaining flow stability despite pressure fluctuations and temperature variations. Valves, regulators, and flow controllers must operate reliably for thousands of hours in the space environment. The pulsed periodic operating mode mentioned in the Rosatom specifications suggests the engine does not fire continuously but rather in pulses. This is common in high-power plasma thrusters to manage thermal loads and extend component lifetime. Pulsed operation means the engine fires for a fraction of each second, perhaps firing for 1 millisecond every 10 milliseconds, achieving an average power of 300 kilowatts while peak power during each pulse might reach 3 megawatts. This pulsed firing must be precisely controlled to maintain stable thrust and avoid inducing vibrations in the spacecraft structure. The frequency and duty cycle of the pulses affect efficiency, thrust, and component wear. Optimizing these parameters requires extensive testing under realistic thermal and vacuum conditions. Erosion of engine components is a life-limiting factor for all plasma thrusters. The high-energy ions and electrons in the plasma gradually sputter away material from electrodes and chamber walls. Over thousands of hours of operation, this erosion can degrade performance or cause failure. The 2400-hour operational lifetime demonstrated in testing represents substantial progress, but the actual degradation mode must be understood. Is performance gradually declining over those 2400 hours? Or does it remain stable until a sudden failure occurs? Can components be refurbished or replaced during the mission? Or is the engine considered expendable? For a Mars mission, the engine must operate reliably for the duration of the outbound trip, and if used for the return journey, double that lifetime is required. Margin must be included for contingencies. A mission requiring 80 days of engine operation would need an engine qualified for at least 120 days, preferably longer, to provide adequate reliability margin. Plasma instabilities can disrupt engine operation. Under certain conditions, the plasma discharge can develop oscillations, turbulence, or other unstable behaviors that reduce thrust efficiency or damage components. Controlling plasma behavior requires careful design of magnetic field geometry, electrode shapes, propellant injection patterns, and power supply characteristics. The Rosatom engine presumably incorporates design features to maintain stable plasma discharge, but these must be validated across the full range of operating conditions expected during a mission. Throttling the engine to different power levels might be necessary for mission flexibility, and the engine must maintain stability across its entire operating range. Power supply design is critical. Converting 300 kilowatts from a nuclear reactor's thermal output to the high voltage, high current electrical power needed by the plasma engine requires sophisticated power conditioning. The reactor produces heat, which drives a thermodynamics cycle converting heat to electricity. This electrical output must then be converted to the specific voltage and current waveforms the plasma engine requires. High-voltage power supplies operating in space must be designed to prevent arcing or breakdown in vacuum. Insulation that works in air can fail in vacuum. Corona discharge and field emission can cause power losses or component damage. Capacitors must store energy for the pulsed operation mode, and these capacitors must be space-rated to withstand temperature cycling and radiation exposure. Power electronics using semiconductors are vulnerable to radiation-induced single-event effects, where a cosmic ray strikes a transistor and causes it to switch state unexpectedly. Radiation-hardened components and fault-tolerant circuit designs are necessary but add cost and complexity. Thermal cycling is another challenge. As the spacecraft moves through its orbit and mission phases, solar heating varies. When near Earth, solar intensity is about 1 kilowatt per square meter. At Mars, it drops to about 400 watts per square meter. The spacecraft structure expands and contracts with temperature changes. The engine must tolerate these thermal cycles without cracking or losing alignment. Materials with different thermal expansion coefficients can create stress at joints and interfaces. Magnetic field coils might shift position relative to plasma channels, changing engine performance. Careful material selection and structural design are required to maintain alignment and performance over the mission duration. Integration with the nuclear reactor requires detailed interface design. The reactor must start up in space, reach operating temperature, and maintain stable power output for months. Reactor control systems must respond to changing power demands as the engine throttles or operates in pulsed mode. If the engine shuts down unexpectedly, the reactor must safely reduce power without overheating. Thermal transport from the reactor core to the power conversion system must be efficient and reliable. Coolant loops, if used, must not leak or degrade. Heat pipes or other passive thermal transport mechanisms must function properly in microgravity where natural convection does not occur. The spacecraft's attitude control system must compensate for the continuous thrust from the plasma engine. 6 newtons of thrust applied off the spacecraft's center of mass creates a torque that would cause the spacecraft to rotate. Reaction wheels or control moment gyroscopes must counteract this torque to maintain desired attitude. Over weeks or months of continuous thrust, the reaction wheels accumulate angular momentum and must be desaturated periodically using thrusters or magnetic torque rods. Propellant for these attitude control maneuvers must be carried in addition to the main propellant for the plasma engine. The attitude control system must also manage any thrust vector misalignment. If the plasma plume does not exit exactly along the engine centerline, a small side force results, requiring continuous correction. Navigation during continuous thrust missions requires different techniques than conventional missions with brief burns and long coast phases. Ground-based tracking provides position and velocity estimates, but the continuous acceleration means trajectory predictions must account for ongoing thrust. Small errors in thrust magnitude or direction accumulate over time, causing the actual trajectory to diverge from the planned path. Course corrections are necessary, requiring the spacecraft to adjust thrust direction or magnitude periodically. Autonomous navigation using star trackers and inertial measurement units helps the spacecraft determine its orientation and acceleration independently of ground contact. Deep space optical navigation, imaging asteroids or planets against background stars, provides position fixes to update trajectory knowledge. All of this navigation data must be processed in real time to ensure the spacecraft stays on course toward Mars. Communication with Earth becomes more challenging as distance increases. At Mars, light travel time is between 4 and 24 minutes depending on the relative positions of Earth and Mars in their orbits. Commands sent from ground control take that long to reach the spacecraft, and telemetry takes equally long to return. This delay means the spacecraft must operate autonomously for short periods, executing stored command sequences and responding to anomalies without waiting for ground intervention. The plasma engine must have safeguards to shut down if it detects problems, and the spacecraft must be able to maintain safe configuration while waiting for ground controllers to assess the situation and transmit new commands. Communication antennas must track Earth as the spacecraft's orientation changes, requiring articulation mechanisms or multiple antennas to maintain contact. The radiation environment in interplanetary space poses risks to both crew and hardware. Galactic cosmic rays are high-energy particles, primarily protons but including heavier nuclei, originating from supernova explosions and other energetic events across the galaxy. These particles have extremely high energies, often measured in billions of electron volts, and penetrate deeply into materials. Shielding against galactic cosmic rays is difficult because thick shielding can actually create secondary radiation through nuclear interactions. When a cosmic ray strikes an aluminum atom in the spacecraft hull, it can fragment both nuclei, producing a shower of secondary particles. Hydrogen-rich materials like polyethylene or water are more effective shields because hydrogen nuclei are single protons that tend to absorb energy without fragmentating. But even with optimal shielding, complete protection is impossible. Crew receive a continuous low dose throughout the mission. Solar particle events are more sporadic but potentially more dangerous. When the sun produces a major flare or coronal mass ejection, it can accelerate protons to high energies and send them streaming through the solar system. These events are somewhat predictable, with increased frequency during solar maximum, but individual events can occur with little warning. A large solar particle event can deliver a radiation dose in hours that would take weeks to accumulate from galactic cosmic rays. Spacecraft must have a shielded storm shelter where crew can retreat during solar particle events, waiting out the peak flux over a few days. Monitoring space weather and forecasting solar activity becomes essential for crew's safety. Radiation also damages electronics and materials. Semiconductors can accumulate displacement damage over time, changing their electrical properties. Solar cells degrade, reducing power output. Optical systems can darken as radiation creates color centers in glass. Organic materials like plastics and lubricants can become brittle. All components must be selected and tested for radiation tolerance appropriate to the mission dose. The nuclear reactor adds to the radiation environment, producing neutrons and gamma rays that must be shielded. Reactor shielding typically uses materials like lithium hydride or borate polyethylene to absorb neutrons, and tungsten or lead for gamma rays. This shielding protects the crew and sensitive equipment, but adds significant mass. Micrometeorite impacts are another concern. Space contains debris ranging from dust particles to small rocks. At orbital velocities, even tiny particles carry substantial kinetic energy. A 1-gram particle traveling at 10 km per second has kinetic energy equivalent to a 1 kilogram mass moving at 100 meters per second, like a baseball thrown at over 200 miles per hour. Impacts can puncture thin structures, damage solar panels, or degrade optical surfaces. Shielding against micrometeorites requires multilayer structures with spacing designed to fragment and vaporize incoming particles before they penetrate to critical components. The plasma engine's electrodes and magnetic coils must be protected, as a micrometeorite strike could short-circuit the system or damage the magnetic field geometry. Life support for a crewed mission adds mass and complexity that affects the overall mission feasibility. Astronauts require about 2 kilograms of food per day, roughly 2 kilograms of water if recycling is highly efficient, and oxygen to breathe. For a 60-day outbound trip, crew members would need about 480 kilograms of food, plus water and oxygen. Modern life support systems recycle water and oxygen with high efficiency, recovering over 90% through filtration, distillation, and electrolysis. But recycling systems require power, spare parts, and periodic maintenance. Carbon dioxide must be removed from cabin air using lithium hydroxide canisters or regenerable systems like the carbon dioxide removal assembly used on the International Space Station. Trace contaminants must be filtered. Humidity must be controlled. Cabin pressure must be maintained. All of these functions require equipment that adds mass to the spacecraft. The habitat structure itself must provide adequate volume for crew comfort and functionality. Studies of long-duration spaceflight suggest minimum volume requirements around 15 cubic meters per crew member to prevent psychological stress. For 4 crew members, this means a habitat of at least 60 cubic meters, roughly equivalent to a cylinder 3 meters in diameter and 8 meters long. Larger volumes improve comfort but increase structural mass. The hull must withstand internal pressure, typically maintained at about 1 atmosphere or 80 kilopascals. It must provide thermal insulation against the temperature extremes of space, ranging from cryogenic cold in shadow to intense heat in sunlight. It must incorporate radiation shielding, meteorite protection, and mounting points for equipment. All of this structural mass must be accelerated by the plasma engine, consuming propellant. Psychological factors for crew on a rapid transit mission might actually be improved compared to conventional longer missions. 60 days in a confined spacecraft is challenging but manageable, similar to submarine deployments or Antarctic winter-over missions. Communication delay increases as the spacecraft moves farther from Earth, eventually reaching about 20 minutes each way near Mars. This makes real-time conversation impossible, requiring asynchronous communication via recorded messages. Crew must be selected and trained for psychological resilience, able to work effectively in isolation with only their crewmates for company. Entertainment, exercise equipment, private sleeping quarters, and adequate lighting all contribute to crew well-being. These amenities add mass but are essential for mission success. Medical contingencies must be planned. If a crew member becomes seriously ill or injured during transit, there is no possibility of evacuation or emergency return to Earth. The spacecraft must carry medical supplies, diagnostic equipment, and crew members trained in emergency medicine. Telemedicine links to Earth can provide guidance from specialists, but the communication delay limits real-time consultation. The spacecraft must be equipped to handle scenarios ranging from dental emergencies to appendicitis to traumatic injuries. Pharmaceutical supplies must remain stable in the space environment for the mission duration. Surgical capabilities might be required, which is extremely challenging in microgravity where blood and bodily fluids do not behave as they do on Earth. Food preparation and waste management are mundane but essential. Food for space missions is typically freeze-dried or thermostabilized to reduce mass and prevent spoilage. Water is added for rehydration. Variety and palatability matter for crew morale over long missions. Waste management in microgravity requires specially designed toilets that use airflow to move waste away from the body. Solid waste is compacted and stored. Urine can be recycled through water recovery systems. All of this requires equipment, power, and consumables. The mass budget for life support, habitat, and crew consumables must be included in the overall spacecraft design and affects the propellant requirement for the plasma propulsion system. Comparing the Rosatom approach to other nations' programs provides context. China has been developing space nuclear technology with increasing ambition. Reports from late 2024 indicated progress on a 1.5 megawatt nuclear reactor designed for space propulsion. Chinese researchers have published papers on plasma propulsion concepts and nuclear thermal systems. China's space program has demonstrated rapid progress in recent years, with successful Mars rover landing, space station construction, and lunar sample return. If China successfully develops high-power space nuclear systems, they could field plasma propulsion capabilities on timelines similar to Russia's projections. The United States has multiple programs underway. NASA's Nuclear Thermal Propulsion Program aims for ground testing of reactor components in the late 2020s. DARPA's Draco program targets an in-space demonstration by 2027, though this timeline may slip. NASA has also funded studies of nuclear electric propulsion using technologies similar to the Rosatom plasma engine. The kilo-power reactor demonstrated feasibility of small space reactors at kilowatt scale. Scaling to hundreds of kilowatts or megawatts remains a development challenge. The United States has substantial nuclear engineering expertise but has not flown a space reactor since the SNAP-10A in 1965. Over 60 years ago. Reconstituting that capability requires overcoming regulatory hurdles, developing new infrastructure, and sustaining funding over multiple budget cycles. Europe has less activity in space nuclear power but contributes to plasma propulsion through Hall thruster development and other electric propulsion technologies. The European Space Agency has investigated nuclear power concepts but has not committed to major development programs. European expertise in fusion research and particle accelerators could potentially translate to plasma propulsion applications, but no major programs currently exist. Japan has advanced space technology but limited activity in space nuclear systems. partly due to political sensitivity around nuclear technology following the Fukushima accident. India has expressed interest in space nuclear power, but has focused primarily on solid rocket motors and cryogenic engines for launch vehicles. The geopolitical dimension of space nuclear technology includes treaty obligations and international norms. The Outer Space Treaty of 1967 prohibits placing nuclear weapons in space but permits peaceful uses of nuclear energy. Any space nuclear reactor must be designed and operated to avoid creating radioactive debris that could endanger other spacecraft or re-enter Earth's atmosphere. International cooperation on space nuclear safety has been limited, with different nations pursuing independent programs. As more nations develop space nuclear capabilities, coordination and transparency become important to prevent misunderstandings and reduce risks. Looking at the broader trajectory of space exploration, rapid transit to Mars represents one capability among many needed for sustained human presence in the solar system. Even with 30-day transits, Mars missions remain expensive and risky. The infrastructure required extends beyond propulsion to include launch systems, orbital assembly, life support, surface habitats, power generation on Mars, communication networks, and return vehicles. A single demonstration mission using plasma propulsion would prove feasibility but would not establish sustained presence. That requires regular flights, pre-positioned supplies, redundant systems, and economic justification. Economic justification for Mars missions remains unclear. Scientific research motivates some missions, but robotic spacecraft can conduct science more affordably than crewed missions. Resource extraction from Mars is speculative, with no identified resources valuable enough to justify transport costs back to Earth. Settlement and colonization are long-term aspirations but require technologies and investments far beyond current capabilities. Most analyses suggest Mars missions in the coming decades will be government-funded exploration programs, similar to Apollo, rather than commercially viable enterprises. This limits the pace of development to what governments are willing to fund consistently over many years. Yet technological progress continues driven by multiple motivations: national prestige, scientific discovery, technological spin-offs, inspiration for future generations, and long-term vision of becoming a space-faring civilization all contribute to sustained investment in space exploration. The Rosatom plasma engine development fits within this broader context. It represents one nation's effort to advance space propulsion technology, potentially gaining strategic advantages in deep space access and demonstrating technological leadership. Whether it leads directly to Mars missions or provides knowledge that enables future systems, it contributes to the gradual expansion of human capabilities in space. The fundamental physics and engineering principles behind plasma propulsion are well established. The Rosatom prototype demonstrates these principles can be implemented in hardware and operated for thousands of hours. The remaining challenges are engineering, making the system reliable, integrating it with spacecraft, qualifying it for flight, and developing the supporting infrastructure. These are difficult challenges but not insurmountable. Similar challenges have been overcome in past space programs through sustained effort and adequate resources. The 30 to 60-day Mars transit enabled by this technology would represent a significant milestone in space exploration. It would reduce crew radiation exposure to levels approaching acceptability for career astronauts. It would shorten mission duration enough to improve psychological feasibility. It would demonstrate capabilities applicable to missions beyond Mars, potentially enabling access to the asteroid belt, outer planet moons, or other destinations currently considered too distant for crewed missions. Each advance in propulsion technology expands the envelope of what is possible, gradually opening the solar system to human exploration. If you appreciate this kind of clear, evidence-driven explanation, subscribing and liking the video helps more of this content reach the right audience. You'll also find many other videos on the channel that follow the same approach, examining space technology and missions based on measured data and verified performance rather than speculation or hype.